Alright, so today we're going to be covering Euler's method, I think it's pronounced Euler, but this guy not only has his own number, but he has his own method. So this is for like a Calculus 2 or AP Calculus BC. This is not in the first level calculus course. So if you're in Calculus AB or Calculus 1, you can just skip this video and go on to the next, because this is more of a Calc BC topic. But let's continue on. So Euler's method is used for approximating a function when you have a slope field. So this is like actually a slope field, but I am not drawing all the slopes because I am lazy. So you have the first point here, and what you're going to do is you look at the tangent line. So let's say the tangent line looks like this. And so then you're going to go by your little gx here. And so whatever your dx is, you go up to that next x point. So you're going to have x, and then you're going to do x plus dx, blah, blah, blah. And so then you look at here, and then you're like, okay, what is the tangent line here? Or what is the slope here? So that's about that. So we don't know that we're not at this point yet, so we're just gonna continue on. We could figure out this tangent line because we're given dy dx. We are in the slope field realm. And then we repeat this process. We look at the slope here, so it's like that. And then here it's like this. I'll do little dots here. And here we started to notice it's going down. And so we get this general shape of the curve with Euler's method. But let's see this in action. Alright, so we have our first little thing here. We have dy dx. We're just going to have it be equal to y for now. Our delta x is going to be 0.1, and that was the little step size, the increase by x that we saw earlier. And this y of 0 is just our initial starting point. So if you wanted to think of this as uh, x comma y, this 1 is your y value, and 0 is your x. So our y-intercept is 1. But let's get started. So maybe draw a table, because again, tables are very useful for visualizing information. So we have our first point, which is 0, 1. And maybe we'll want to have a column for our slope here. And in this case, it's just, I'll write y prime for our dy dx. It's the same thing in different notation, y prime. And here it's just the same as our y, so, which is 1, but it may not be the case every time. Instead of our dy dx, we're just going to have a dy. I think that's going to be the better way to explain this. So this is going to be our dy dx times our delta x. That looks abysmal. Let's try that again. Dy dx times our delta x. And if delta x is really small, then this is basically dy. And this is what calculus is getting this delta x as close to 0 as possible. But let's continue on. So our dy is, let's see, 1 times 0.1. So that's 0.1. And so then we can now go to calculate our new x and y. Well, our new x is easy. Our new x is just x plus delta x. So it's just going to be 0.1. 0 plus 0.1 is 0.1. And now we have to add y and dy. So now that's 1.1. So now we have our new y value by just adding on to this. And now we can do the same thing again. We look at this, our slope is dy, so that's going to be 1.1. That is 11. 1.1 times our delta x, which is going to be 0.1. So this is equal to 0.11, right? We're going to go add delta x to our x. And so now we add these numbers together to get our new y. So that's 1.1 plus 0.11. And so that is 1.21. And then we continue. So our dy dx is just 1.21 here times, and we're going to multiply it by 0.1, which is, this is 0.121, and then we're going to add that back over here. 0.3, and that would be 1.331, just by adding these two numbers together. And so if they ask for 3 points other than the starting ones, you could plot these points, or you could say these points. So all of these are points that would be on that general solution. It's not very specific because our delta x is not 0, but this is a way to approximate that curve. All right, let's do one more because these are a bit confusing. So let's create our little table of x, y, and dy. That is a wonderful y we have there. Dy, boom, boom. All right. So our first point is 3, 1. And now we will say this is x squared minus y. So let's substitute that in. And we're just going to go to 3 additional points. So 1, 2, 3. So this is x squared, which is going to be, let's write 3 squared here, minus 1. And then we're going to multiply by our 0.5, or 0.05, 0.05, which is our delta x. So this value is 0.4. And so we're going to now increase our x by 0.05. And so this is 3.05, 3.1, 3.15, and I'll just leave it right there. So we know how the x is going to increase. And so now we add 1 and 0.4, so that's going to be 1.4. Is going to be a point. And then we are going to do this exact same thing again. So we're going to say 3.05 squared, because this is our x squared term, minus our y, which is 1.4. And then we're going to multiply all of this by 0.05, which is about 0.39395. And my best suggestion is if you're allowed to use a calculator, go to like 5 decimal points. So 1, 2, 3, 4, 5. So that's 3. Just and then you add this back to your 1.4. And I don't have enough room here, so I'm just gonna write like 1.795. And then I will continue this for the rest of them. So here it's our 3.1 squared minus our y times our delta x. It's 3.9, add that is 2.18. And so that was Euler's method.